Good morning, everyone. Myself, Dr. Krishnamurthy, working as Assistant Professor in the Department of Chemistry, JSS Art Science and Commerce College, Gokak, which is affiliated to Ranichanama University, Belagavi. Last class, we discussed about the properties of transition metals, that is electronic configuration, melting point and boiling point, enthalpy of atomization, atomic and ionic radii, oxidation state and magnetic behavior. Today we'll discuss about the remaining properties one by one in detail. So transition element exhibits colors due to the presence of unpaired electrons. As we already know, transition elements nothing but, or transition metals nothing but, they are partially filled d orbitals, that is incompletely filled d orbitals are called transition elements. The unpaired electrons is responsible for the color. When an electron from a lower energy d orbital is excited to a higher energy d orbital, the energy of excitation corresponds to the frequency of light absorbed. Here, the electron which absorbs energy from the light and they promote it to higher energy level, lower energy to higher energy, lower energy, that is ground state, that is T2G, then it is promoted to higher energy level, that is EG. Then the energy of excitation corresponds to the frequency of light absorbed. This frequency generally lies in the visible region. The color of the observed corresponds to the complementary color of the light absorbed. This is very important. The color observed corresponds to the complementary color of the light absorbed. The frequency of the light absorbed is determined by the nature of the ligands. So as we know, most of the transition metal compounds, ionic as well as covalent, they are colored both in solid state and in aqueous state. So generally the elements or the ions having unpaired electrons produce colored compounds. This is very important. Unpaired electrons are responsible for the colored compounds. If it is no unpaired electrons, then it is colorless. In case of zinc 2 plus and cadmium 2 plus, these are D10 system. Zinc 2 plus 3D10 and cadmium 2 plus, that is 4D10. D orbitals are completely filled. This is one case. And titanium 4 plus, here all d orbitals are vacant. Titanium is 22, atomic number 22. It lasts 4 electrons. There is no electrons in the d orbitals. D orbitals are vacant. In these two cases, here d orbitals are completely filled. Here d orbitals are empty or vacant. In this case, there is no DD transition occurs. Therefore, they do not absorb radiations, so they are colorless. If d orbitals are completely filled or empty filled, empty, then they are colorless. In between, that is partially filled d orbitals exhibits color. If the colored compounds, they have DD transition. So this is a table containing a list of transition metal ions, particularly 3D series. This is a corresponding configuration and the number of unpaired electrons and the corresponding colors. Scandium 3 plus and titanium 4 plus. The electron configuration is 3D0. No electrons in the d orbitals. Therefore, these ions are colorless. Titanium 3 plus, vanadium 4 plus, configuration 3D1. There is one unpaired electron. It exhibits color blue or purple. Vanadium 3 plus, 3D2, two unpaired electrons, green in color. Vanadium 2 plus and chromium 3 plus, 3D3, three unpaired electrons, it is violet color. Manganese 3 plus 3d4, unpaired electrons 4, violet color. Manganese 2 plus, iron 3 plus 3d5, 5 unpaired electrons, it is pink or yellow color. Iron 2 plus or cobalt 3 plus 3d6, 4 unpaired electrons, green or pink color. Cobalt 2 plus 3d7, there are 3 unpaired electrons, it is pink in color. Nickel 2 plus 3d8, 2 unpaired electrons, green color. Copper 2 plus 3d9, 1 unpaired electrons, 1 unpaired electron, blue color. Zinc 2 plus and copper plus 3d10, no unpaired electrons. It is therefore it is colorless. So here there are transition metal compounds exhibit different colors. So this is scandium oxide and titanium oxide. They are colorless due to empty d orbitals. Empty d orbitals. D orbitals are vacant. Vanadium sulfate dihydrate. It is light blue in color. Sodium chromate, yellow color. Manganese chloride tetrahydrate is light pink color. Potassium ferricyanide, orange color. Cobalt chloride, the pink color. Nickel nitrate, hexahydrate, green in color. Copper sulfate pentahydrate, blue color. Zinc sulfate heptahydrate, this is colorless due to the completely filled d orbital. Next property, standard electrode potential. Electrode potentials are the measure of the value of total enthalpy change. Electrode potentials value depends upon enthalpy of atomization and also the enthalpy of hydration. Lower the standard electrode potential, the more stable is the oxidation state of the metal in aqueous state. So lower the electrode potential value, more stable is the oxidation state of the metal. So here we observe a standard electrode potential values with respect to the 3D series elements. Vanadium minus 1.18, chromium minus 0.91, manganese minus 1.18, iron minus 0.44, cobalt minus 0.28, nickel minus 0.25, and copper plus 0.34. Here the value of manganese and vanadium is same, minus 1.18. It is much less. The enthalpy of what is that standard electrode potential, it is much less for manganese and vanadium. So in this graph also we observed standard electrode potential against 3D series elements. Here copper as positive, that is plus 0.34, and therefore greater amount of energy is required to transform copper into copper 2 plus. Copper into copper 2 plus. Then the stability of the off filled D subshell in manganese 2 plus and the completely filled D10 configuration in zinc 2 plus. Manganese 2 plus off filled, that is D5, and zinc 2 plus is completely filled, that is D10, or related to their inert values, whereas inert for nickel is related to the highest negative enthalpy of hydration. The low value for scandium reflects the stability of scandium 3 plus, which has a noble gas configuration, that is argon. Scandium 3 plus, nothing but the argon configuration. The highest value for zinc is due to the removal of an electron from the stable D10 configuration of zinc 2 plus. The comparatively high value for manganese shows that manganese 2 plus, that is a D5 configuration, is particularly stable, whereas comparatively low value for iron shows the extra stability Fe3 plus, that is a off-filled D5 configuration. So next property, chemical reactivity. Transition metals vary widely in their chemical reactivity. Many of them are sufficiently electropositive to dissolve in mineral acids, although a few are noble, that is, they are unaffected by simple acids. The metals of the first series, with the exception of copper, are relatively more reactive and are oxidized by 1 molar H plus. Though the actual rate at which these metals react with oxidizing agent like hydrogen ion is sometimes slow. The inert values for uh, metal ion or the metal indicate a decreasing tendency to form divalent cations across the series. This general trend towards less negative inert values is related to the increase in the sum of the first and second ionization enthalpies. It is interesting to note that the inert values for manganese, nickel, and zinc are more negative than expected from the general trend. Next, the inert values for the redox couple, that is the tripositive ion and dipositive ion, shows that manganese 3 plus and cobalt 3 plus, these are tripositive cations, are the strongest oxidizing agents in aqueous solutions. Whereas the ions titanium 2 plus, vanadium 2 plus, and chromium 2 plus are strong reducing agents and will liberate hydrogen from a dilute acid. So here is the example. Here chromium acts as reducing agent. It reduces hydrogen to H plus to hydrogen and itself oxidized to chromium 3 plus. So next, very important catalytic activity. The transition metals and their compounds are known for their catalytic activity. This catalytic activity of transition metals is due to the following reasons. Number one, because of their variable oxidation state. We already know transition metals shows variable oxidation state. Number two, presence of unpaired electrons in their incomplete d orbitals. Third one, some transition metals provide a suitable surface for the reaction to take place. For example, vanadium oxide V2O5 in contact process for the manufacture of sulfuric acid. Here vanadium oxide acts as a catalyst. Next, finely divided iron in Haber's process for the manufacture of ammonia. Nickel acts as a catalyst in catalytic hydrogenation of oils, and cobalt in the synthesis of gasoline. So these are some examples. In addition, transition metal ions can change their oxidation states. They become more effective as catalysts. For example, iron catalyzes the reaction between iodide and persulfate ions. Iodide and persulfate ions, here iron acts as a catalyst. So next, complex formation. Transition metal ions form a large number of complex compounds. It exhibits thousands of complex compounds. Complex compounds are those which have a metal ion linked to a number of negative ions, that is anions, or neutral molecules that have lone pair of electrons. These ions or molecules are called ligands. They donate lone pair of electrons to the central transition metal ion, forming coordinate bond. Here ligands are electron rich species and the transition metal ions are the electron deficient species. So ligands donate electron pairs to the central metal ion to form a coordinate bond. A few examples are given below. Hexacyanoferrate 3 or hexacyanoferrate 2 or tetramine copper 2. Here tetramine zinc 2, tetracyanonickelate 2, then tetrachloroplatinate 2. Many examples, such complex compounds are not formed by S and P block elements. So these complex compounds or coordination compounds followed by D block elements. The transition elements form complexes because of the following reasons. Number one, comparatively smaller size of the metal ions. Second one, their high ionic charges. Third one, availability of vacant d orbitals so that these vacant orbitals can accept lone pairs of electrons donated by the ligands to form coordinate bond. Therefore, the transition metals form innumerable number of complex compounds or the coordination compounds. So next property, interstitial compounds. The transition metals form a large number of interstitial compounds in which small atoms such as hydrogen, carbon, boron, and nitrogen occupy the empty spaces, that is, interstitial sites in their crystal lattices. They are represented by formula like titanium, carbide, titanium hydride, etc. However, actually they are non-stoichiometric materials. Example, titanium hydride, vanadium hydride, etc. And the bonds present in them are neither typically ionic nor covalent. Some of their important characteristics are as follows. Number one, they are very hard and rigid. For example, steel, which is an interstitial compound of iron and carbon is quite hard. Similarly, some borides are as hard as diamond. They have high melting points which are higher than those of pure metals. They show conductivity like that the pure metal. They acquire chemical inertness. This is about the interstitial compounds. So next, alloy formation. Alloys are homogeneous solid solutions of two or more metals obtained by melting the components and then cooling the melt. These are formed by metals whose atomic radii differ by not more than 15%, so that the atoms of one metal can easily take up the positions in the crystal lattice of the other. Now, yes, transition metals have similar atomic radii and other characteristics. So, as we know, transition metals have similar atomic radii and similar characteristics, hence, they form alloys very readily. Alloys are generally harder, they have higher melting points and more resistant to corrosion than the individual metals. The most commonly used are the ferrous alloys. The metals chromium, vanadium, molybdenum, tungsten, and manganese are used in the formation of alloy steels and stainless steels. Some alloys of transition metals with non-transition metals. Transition metals with non-transition metals are also very common. For example, brass, it is a mixture of copper and zinc, and bronze, it is a mixture of copper and tin. Here, copper is transition metal, and zinc and tin are the non-transition metals. So, we observed a innumerable number of characteristic properties of transition metals. The main reason is the presence of unpaired electron. Transition elements exhibits a number of characteristic properties is due to the presence of unpaired electrons. Thank you.